as I said, we start light with a little bit of like hardcore natural language processing. Tomek, please come.
All right, so thank you for the introduction. And I guess I have to open up my slides first. Perfect. Okay, so thank you for the introduction, Jeff. And I have the honor to present the first speech at the first STX Next Tech Summit, so it's pretty cool, right? And today I will be speaking about the processing of natural language using Python, and a little bit of machine learning as well. So at first, let me present the agenda of the presentation. I'll tell you what you need to start your adventure with processing natural language and doing machine learning with Python, introduce the packages, the libraries that we'll use, and then we'll do a little bit of machine learning itself in Python, some code examples, nothing hardcore, but machine learning in its true form. And then we'll move on to natural language processing. We'll define it as a problem. We'll say a couple of words about what are the main tasks, main solutions, the main things that we have to do in order to process natural language. And then we'll move on to some examples in NLTK, which is a well-known Python library for doing just that. So if you want to start your adventure and you want to start doing natural language processing with Python, or computation linguistics, for instance, and you don't want to deal with installing all those packages and this boring stuff, compiling packages, compiling libraries, then you can just download Anaconda, which is a pretty awesome piece of Python framework. It's got all you need. It's got all the libraries. It can be installed in parallel to your current Python packages and Python distributions. It's completely free. It works on all the platforms. And yeah, it's got even some tools to connect with Excel, right? So please check it out because it's really, really fine for this task. So what does it contain? It contains around 200 packages for doing scientific computations, for doing data engineering, and all that stuff. But we're mainly interested in language, right? So what we need is NumPy, SciPy, Matplotlib, scikit-learn, and NLTK. And they're all contained within this single Python framework. Couple words about each of them. Well, NumPy, you probably know it already because it's a package for doing some mathematics, data science. So it contains some n-dimensional arrays. SciPy is built upon NumPy, and it just extends it. It's got some high-level features, high-level methods. It's just easier to work with than NumPy. And Matplotlib is just for charting, for doing charts and plots. And then scikit-learn is the Python for machine learning. And NLTK stands for Natural Language Processing Toolkit. So first, let's begin with machine learning. This is scikit-learn. And as I said, you can do machine learning. You can do artificial intelligence with it. It's got some simple tools. You don't have to be an expert in the artificial intelligence field. So you can just easily go through the documentation, read about some classes, some methods, and experiment with it, and build your first systems. It's accessible to everybody, as I said. And it's also built on NumPy, SciPy, and Matplotlib, the thing for charting, right? So a bit of revision. So what is a machine learning problem? Well, if you get a set of n samples of data, you want to predict some properties of these samples, right? So let's say we get a bag which is filled with fruits, and you just pick one fruit and you cannot look at it. You can just touch it and see how big it is, how much does it weigh, and you want to know if it's an orange or an apple, right? So you can approach this problem in two ways. You can get a training set of data, so you can get a bag of fruits and you can just open it up, pick up an orange and see how heavy it is and how big it is, what's the texture and so on. And based on that, you can apply what you've learned to another unknown set of data, right? So you get a bag of fruits that is closed and you don't know what you're going to pick, but you already know the weight of an orange and you know what it should feel like. So you can apply this knowledge for predicting the properties of this unknown data. The other kind of approach is you don't really know what's inside. You haven't really seen any fruits in your life before. And you know that some things are heavier than the other ones, right? So maybe there's like 2 kinds of fruits inside. Maybe there's 3 kinds of fruits. And that's unsupervised learning. And the previous one was supervised learning, right? So some examples. That's classification. That's the first kind of supervised learning. So first you get the bag of fruits, you open it up, you check out the weights and sizes and texture. And you know that inside of this bag there should be apples and oranges, right? So you're trying to classify each object into one of these categories. You're trying to pick a fruit and put it in the apple bag or in the orange bag. And regression is a bit more difficult in the theoretical kind of sense. because you're not trying to put the fruits into categories, right? But you're trying to predict some real values. So based on the color of the fruit, how ripe it is, you're trying to predict how heavy it would be, right? So you're dealing with real numbers instead of discrete categories. This is unsupervised learning. So that's the problem when you take a bag of fruits and you don't know what's inside, you have never seen a fruit in your life before, and you don't know what kind of species there are. So you got some data, you get some properties or features of this data. So here we have a set of different flowers. It's iris flowers. And you get a sepal length, sepal width, and petal length. Petals are, just the flower petals. And sepals, I checked it on Wikipedia, that's those little green things that grow like just below the flower. You can check it on Google Graphics if you don't know what I mean. And based on that data, you're trying to guess how many flower species or flower categories are there. So this is one kind of clustering or classification you can do. And that's another one. And you don't know how many species are there. So that's the solution, right? There's 3 kinds of iris flowers. And it's really hard because you don't know what you're dealing with, and you have to apply some guessing, some heuristics and stuff. And to make things maybe more clear, or maybe the other way around, maybe we'll make it a little bit more complicated. We'll go through an example with a naive Bayes classifier, and we'll try to classify some texts. So we'll take a text, which will come from a newsgroup. It will be a newsgroup article, newsgroup post, and we'll try to guess in which category or which newsgroup it came from. Was it computer graphics or, let's say, religion, for instance, right? So to do it, first we have to load our data into some kind of reasonable data structures. Second of all, we have to extract the features, right? So we have to get the text as an apple and extract its weight, its texture, and all that stuff, and also put it in some kind of reasonable data structure. And at the end, if we have the features ready, we can start with the training of our classifier. So as I've mentioned, we use a very well-known, among data scientists, very well-known data set. It's called 20 newsgroups. And it contains around 20,000 newsgroup articles, which are almost evenly placed across 20 different newsgroups. It contains religion, it contains society, science, computer graphics, and all that stuff. On the right side, yes, on the right side, you can see an example. It just looks as a usual newsgroup post. So it's got the header and the content, and it's unprocessed. The text is in its pure form with all the mistakes and all the fancy newsgroup formatting, right? So let's go into the code and see what happens. We'll choose 4 categories for our sample. So we'll choose atheism, Christianity, graphics, and science, medicine. And we can just import a special method from scikit-learn, which will fetch the training data for us. So we fetch some text from the subset is called train, because those data sets that are contained within scikit-learn are already prepared for us to do it easily, right? So we don't have to deal with all the text processing, with all the data processing. It's just there for us to develop our algorithms and then test them, right? So we choose the subset train. We choose our 4 categories to make things more simple, so we don't deal with all the 20 newsgroups. And we tell scikit-learn to shuffle around things, so it's not that easy and it's not that predictable, right? And if we print out the categories of the first 3 data samples we got, we see that it really contains computer graphics, and religion. And if we go further, we'll see the other categories, right? The next step is feature extraction. Feature extraction, as I mentioned, is getting the data of a sample. So weighting the orange, getting its texture, getting its size, and getting all the information about the sample that we'll need to somehow reason in which category it should belong, right? And what kind of features do we or can we use for text data? Well, the first thing that comes to our minds is probably the counts of words, right? Because how do you differentiate between a newsgroup article from a computer, let's say, computer graphics group and a makeup newsgroup? So the computer articles will probably contain words like algorithm and programming and compiler and all that stuff. And they will have high counts, right? And if you read through makeup articles, they will probably not contain words algorithms and, I don't know, data structures, right? They will contain words like lipstick and, I don't know, whatever. I just don't read through them. So, yeah, we can use a special class that is in scikit-learn. It's called count Vectorizer. And we just get our data, we instantiate this class, and it gives us a very cool method. It's called fit transform. We just feed it with our data, and it will generate a special two-dimensional array, a matrix, that will contain a word count for each word in each of the dataset articles, right? So we'll know that in the second article, which is from the news group Computer Graphics, the word algorithm appeared that many times, and the word lipstick appeared, I don't know, 2 times maybe. It happens, right? And then once we have the features extracted as counts, maybe we should do a little bit more thinking about, is it a proper feature to base our algorithm on? Because you can imagine that a text that has only 2 words and contains a word algorithm once is not really equal to a text that contains few million words and also contains the word algorithm once, right? Because the long text, maybe somebody was citing somebody or they just misused the word algorithm. And the short text, if it has only 2 words and one of the words is algorithm, then the probability that this text came from a computer graphics forum is really, really high, right? So word counts, maybe not in this case. Let's use word frequencies, right? But the problem with word frequencies is also that, let's say in English, some words appear more often than others, right? When I speak, I use the word I, am, the, a, all the articles or the pronouns and stuff more frequently than the other words, right? So let's normalize the frequencies with the global frequency rate for each word. I don't know if you're following, but we'll see that later, right? This is just the hardcore code example. And we got a special class for that. It's called TF-IDF transformer. And if we feed it with our word counts, we'll get back the word frequencies normalized by their global frequencies, which are basically called TF-IDF. It stands for text frequency, inverse document frequency. It's a known measure in data science. We don't have to go into too much details, but we can notice that once we had our matrix that contained only the word counts, it was in this shape. So that's the size of this matrix. And once we transformed it into TF-IDF, it didn't shrink, it didn't grow. It's the same, it's just kind of we measure the features changed, right? So once we have the features ready, we can start the training. And that's the hardcore part, right? We use a naive Bayes classifier. And what is a naive Bayes classifier? Well, it's the most basic approach to machine learning. So you just use the Bayes theorem. I don't know if you still recall that from the mathematics class. So naive Bayes, in the, I don't know, really simple words, is, states that if you know what's the probability of a person having a flu also having a fever, and you know the probability of a person having a flu, and you know the probability of a person having a fever, then you can calculate the probability of a person having a fever also having a flu, right? So you just mix things up. So we use that in the Bayes classifier. And why is it naive? Well, basically that it's because of the fact that naive Bayes classifiers assume that the features are independent, right? So if we do our little experiment with the fruits, we take the fruit out of the basket, we assume that the size is independent of the color, right? And the color is independent of the weight. And in many cases, it doesn't really work like that. But for our case, that's just a really good assumption. So what we do is we just get another class from scikit-learn, which is called multinomial naive Bayes, and another hard word, multinomial. It's just because most of the naive Bayes classifiers assume that the distribution of the samples is Gaussian, it's normal. But if you think about text documents in news groups, you will know that if you print it out as a chart, most of the frequencies and most of the word counts don't look as a Gaussian, they look like a histogram, right? So a multinomial function would probably be better, right? So that's why we use it here. But it's not really important. So we just get 2 new strings, God is love, and OpenGL on the GPU is fast. So we can classify them, obviously, right, to 2 categories, Christianity and computer graphics. And we have to do all the stuff again. So we have to, that's our new data. So that's the unknown data. We don't have the features yet. We don't know which categories they fall into. So we have to first extract the counts, then transform the counts into word frequencies and normalized word frequencies. And then we can just use our classifier that was trained before to predict the categories for the new input, right? And as you can see, when we print out the categories that were classified, God is Love really falls into Christianity, and OpenGL falls into computer graphics. So wow, our algorithm works. And that was the easiest I could find. The main problem with that is that you have to do all the things again and again for new input, right? So you have to extract the features, you have to convert the features into some reasonable format, you have to do all the classified training and classification and so on and so on and so on. And if you don't want to do it again and again, you can just use a special class in scikit-learn which is called pipeline, and it just acts as a pipeline. You feed it with data and it goes through all the classifiers and all the workers that you have specified. So as here, we have our count vectorizer, which counts the occurrences of the words. Then it transforms it into a text frequency form, and then it classifies it or trains it, right? Once we have our classifier ready, and we've put some input, some test input, we've seen that it works or it works not too good, we can print out some statistics. So our mean for this experiment was 0.8, which doesn't really tell us anything, but it tells us that it works with more than statistical significance. But if you need some more statistics, some real data science measures, then you can just import another package which is called metrics. And metrics will print out all the measurements that you need. So precision, recall, F1, whatever they use. Confusion matrix, you can just put really nice data into your paper and go through all the conference with these numbers, right? And at this point, you're probably wondering, why is he talking about that? Why do I need all that? Isn't natural language processing just processing text? So like counting the letters and counting the words and doing all that and like dealing with strings? Well, it's not, because if you look at language, it's got many levels. And this is an oversimplified model of the structure of language. Because if you imagine how people communicate, so at first I generate a sound wave, right? And the sound wave enters your ears, and you're trying to somehow deal with the sound wave. So you have to classify some units from this sound wave into linguistically meaningful units, which are phonemes, right? So A, B, T, D, and so on. And once you have those units, you have to put them together to make words. And that's what morphology stands for. And once you have the words, you have to put them in some order and do some reasoning about syntax structure, sentence structure using syntax. Once you have this sentence or phrase, you have to reason, you have to know its meaning, so literal meaning, right? If I say natural language processing is great, then you will know that I want to inform you that natural language processing is great, indeed, right? But if you hear this sentence in this particular context, so at the STX Next Summit, #1, you will know that this is not really supposed to be informative, but it's an example which I used for exemplifying the thing that I'm talking about, and so on and so on and so on. So that's pragmatics, right? Things never mean what they're supposed to mean. If you say, if your girlfriend asks you, do you want to go out? And you say, yeah, it doesn't mean you want to go out. You just want her to stop talking, right? And if you look at those levels of language in a natural language processing system, that's a pretty complete system. And I don't know if it's obvious or not, but it's a dialogue system. So it goes both ways, right? It listens to the speech input, and it processes the input. So it turns the speech sound wave into phonemes and so on and so on and so on, all the way until the proper pragmatic meaning. And then it does some reasoning, some dialogue management, and so on and so on. And it goes back to the user, planning an utterance, planning the answer, doing the syntactic realization and speech synthesis, right? It's also an oversimplification, but that should answer the question, do we really need all that heavy code and machine learning and all those algorithms in natural language processing? So to some point, yes, it is text processing, but if you look at language as a language, which starts from a sound wave and ends up as an idea in your head, well, you might need all those machine learning algorithms, right? And it's funny how it started, because in the 50s, they did an experiment in which they tried to translate 60 Russian sentences into English using a rule-based system. That was developed on a computer that was probably would fit into this room, or maybe not even in this room. And they just put in a punched card which contained an encoded Russian sentence. And the computer was working for a couple of minutes, and it spat out translation, English translation. And it all worked great because the grammar, the rules they used, for parsing this input was trained on the very similar data that they used as input, right? So the computer was expecting sentences and words and grammatic constructions that it already knew, right? So it's not that really complicated. So they just said, wow, that was really simple. And I guess in like 3 or 5 years, we'll have talking computers and like reasoning computers, right? And if you look at these two gentlemen on the left side and see the grin on their faces, they already knew that it's not going to happen, right? I don't know if you recognize them. The first guy is the famous movie star. He starred in the imitation game, Alan Turing, and he basically also invented computer science and the computer program. And Noam Chomsky is people say he's the biggest and greatest linguist of all times. And he also did his work in computer science because, well, he kind of formalized the formal languages and built a hierarchy of computer languages, which means that he gave birth to regular expressions and so on and so on and so on. So thanks to these two gentlemen, we're having this conference today, I guess. And why did we move from rule-based systems to machine learning systems? Well, rule-based systems were good at the beginning. They could do some work, and they're still fine for doing computational linguistics, right? So trying to explain how language works and doing some proof of concepts on the computer. So you come up with a model of language, build rules for, let's say, like semantic reasoning, and you want to put it in the computer and prove that it really works, right? So the computer can reason about language using those rules. But if you're working in the natural language engineering field, you don't want to explain how things work. You just want to make things work, right? So why not just take statistics and instead of trying to explain how things work, just take the things that actually work, model them statistically, and put them into the computer, right? So that's what machine learning techniques do in natural language processing. And we're approaching another piece of code. And I've chosen discourse analysis from all the levels of language as our example, because most of the other levels of language, starting from, let's say, acoustic phonetics, morphology, syntax, and all that, they can be pretty easily based with a finite set of machine learning and rule-based approaches. So you can just take, I don't know, 5 of them, and you'll have all the language dealt with, right? But discourse analysis is a bit different. That's the part when you take the literal meaning, and you're trying to come up with all the meanings that come to your mind and fit them into the sociological context and the cultural knowledge that you have, and all the deep knowledge about the world outside of the language you have, all the empathy that you have and machines don't have. And that's really hard to do, right? And maybe a couple of words about discourse. So discourse, the word stands for conversation, but it also means all the possible ways that the conversation might be understood, right? So if I start speaking right now, again, and I say, John is a boxer, and all boxers like to pee on a hydrant, then you will think for a while, and you will think whether John is a boxer who punches people for money and likes to pee on hydrants, or is John a boxer who is a dog who likes to pee on a hydrant, or all the other ways, right? So discourse contains all that, and that's what discourse analysis does. It goes through all the threads and tries to analyze what the input really meant, right? And that's why we start using NLTK. It's got some cool tools for doing all the tasks in natural language processing, so classification, stemming, tagging, you name them. And it's got also tools for doing discourse analysis, right? So basically, if you use NLTK, you can cover all the tasks involved in constructing a fully functioning dialogue system. Another cold example, I hope you can still bear with me. This will be a bit easier. So let's take another example, which is kind of similar to the one I've just mentioned. A boxer walks, and every boxer chases a girl, right? Let's not get too much into the code, but let's just say that we use a tool from NLTK, Discourse Tester, which can do all the processing, all the listing, all the reasoning for us. And let's see how it works. So we take these 2 sentences. We can list them once we instantiate this class, right? So they got their indexes as 0, as 1. And we can also list the grammar, because we need grammar to process language, right? This is a very simple grammar, and it's not the whole grammar, it's just the first couple of lines that I cut through them for brevity. This grammar is really simple. It just says that sentences are constructed from nominal phrases and verb phrases, and that nominal phrases may be either proper names, or nominal phrases can be either a determiner and a noun, right? So if you try to analyze a sentence, it should have two parts, right? So John is a boxer, should have a nominal phrase and a verb phrase. So nominal phrase, John, should fall into the second nominal phrase type, which contains only a proper noun, right? Is a boxer, is a verb phrase. We don't have verb phrase listed here, but you can believe me, just please do. And once we have instantiated our discourse analysis tool with these two sentences, we can see what are the all possible readings for these two sentences, right? So as you can expect, the first reading for the first sentence is that boxer, which here stands for a person punching for people for money, walks. And the second one is a boxer dog walks, right? So these are the two possibilities. And same for the second sentence, it's just the ambiguity between the word boxer, right? And if we want to see how many possible interpretations of the discourse there are, we can use a readings method with a parameter threaded, right? So these are called threads. So the first possible solution of this discourse would be sentence one, reading one, right? So boxer, the person, walks, with sentence one, reading one, boxer, dog, exists and chases a girl that also exists, right? And all the possible combinations listed below. And what we're trying to do is we're trying to somehow reason which reading is the most probable, and we're trying to eliminate the ones that are, well, not too probable, right? It's also got some cool methods, the discourse tester class from NLTK, which will give us the logic model for our discourse. It's not too interesting, so I guess I can just skip over it. It gives us the logic representation in some kind of notation, and we can, looking at that, if you have some practice, you can see which cases are possible, right? So dash stands for negation, and zeros and ones are indexes for, let's say, cases. So let's mix up things a little bit, and let's add another sentence and see what happens, right? So we just add another sentence, which is John is a boxer to our set. So we have three sentences right now. A boxer walks, every boxer chases a girl, and John is a boxer, right? We can list the readings as we did before, right? So the all possible interpretations of the sentences we have. And we can see that the number of threads grew, right? So it's really, really complicated right now. We don't really know what's happening, right? And what happens here is if you don't want to look at the threads in this really non-human readable notation, the last couple of lines on this slide, you can just use a normalized method which will print it out with a more human readable form, right? Let's move to another example. A student dances, every student is a person. It will exemplify the same fact, right? So if we add a sentence, no person dances, we can pretty much already say that this discourse is what? Is inconsistent, right? Because if we stated that a student dances, so there exists a student who dances, and that every student is a person, then we have stated that the student that exists is a person, and he also dances, right? So saying that no person dances, well, it doesn't really make sense in this context, right? So that's what consistency checking is for. And we can just do that and see if our discourse is consistent after adding another sentence. And of course, it just says that the discourse is inconsistent, and it lists all the readings in which it happened, right? And the dash stands for negation. And if we move further, we can just list the model to see that there's something wrong going on, but let's keep the models, they're not really interesting for us right now. Another thing that is useful in discourse analysis is that if we have some sentences that were already spoken, right? So no boxer chases a girl, John is a boxer, and we add another sentence. We want to check not only if its discourse is still consistent, but we also want to check if this sentence is informative, right? Because once we have some knowledge, once we have some sentences and their interpretations, we can infer new information in the logical kind of sense, right? So if I say a student dances and every student is a person, then saying a person dances is kind of obvious, right? Because if student dances and he's a person, then it's kind of obvious that the person dances, right? There is at least one person that dances. Another example, let's just stick with the boxer kind of examples. And Vincent is a boxer, Fido is a boxer, Vincent is married, Fido barks. Wow, that's a bit dangerous, right? So we have to deal with it somehow. We can list the readings and the number of threads and so on and so on. And in order to deal with cases like that, where we're not really sure if it's possible that Fido, who is a boxer dog, could be married, because we don't know that, we're just machines, right? We have to introduce some background knowledge. So we can just input a file that contains some rules, logical rules, that tell us that if X and Y are married, then X is a person, and Y is a person, and X is not Y, right? Because you cannot be really married to yourself. And that's what we do. We just input some background knowledge, and you can see the rules that I've just mentioned, right? Which says that boxer dog is a dog, boxer is a person. It's not possible, so the negation, that X is a dog and X is a person. Well, things happen, but I'm not really sure if we should include that case, right? Edge cases. And also the thing about being married and about barking and so on and so on and so on. And as you can see, once we included the background knowledge, which is kind of obvious for us, but not that obvious for machines, we have reduced the number of readings to just one, right? And that was our aim. And we can go further. We can just list the models and see that there's no model for Discourse 0, 2, and 3. And we just ended up with one model, one thread for this particular discourse. So what we did, it wasn't really clear, maybe, a lot of code, but we have just reasoned about the discourse, right? So we have applied some background knowledge, we have applied some grammar and some natural language processing, and to do some logical inference, and we have came up with the actual meaning of what the person was trying to communicate speaking these couple of sentences, right? That's just another kind of listing that once we have input the background knowledge, out of these 4 discourse interpretations, only one is still consistent, right? So that's our solution. I know it was really code heavy, and I went through it really fast, but I hope that you at least got a basic understanding or a basic idea about machine learning and natural language processing. And if you're trying to, if you're wondering if NLTK is good for like producing like really real and working natural language processing systems, well, probably not, because it just gives you the idea. It gives you tools to play around and to mess around, to mix things up, see how things work, go through the documentation, see how multinomial naive Bayes classifier differs from conditional random field and all the different weird names that they use in data science. And it's a good starting point. So if you want to start with natural language processing and do a full system, probably look somewhere else. If you want to just use NLTK in your project that is not really based on natural language processing, and you just want to do one task like named entity extraction, well, NLTK might be just for you. So thank you, and I hope I didn't just bore you to death with this speech.
Okay, maybe some questions before the next talk. Do you have any questions for Tomasz? There is a question. Maybe we need another microphone. I will give mine.
Does this library also support different languages than English? Because you've said that there are some set of grammar rules, but each language has a different set of rules.
As far as I know, some of the main languages like Spanish and English, of course, right, are included in NLTK. But those grammars they have are good for some specific domains, right? They're good for some specific applications, and pretty much for testing and just like system prototyping. So if you really want to get serious about processing grammar, it would be reasonable to build your own grammar from scratch, right? Most of the grammars, you don't really start with a blank page. You just take English grammar, see how things work, and you can build a grammar for a similar language. So let's say German or I don't know, Dutch. If you want to build a Polish grammar, you should look for a Polish grammar online. If you don't find one, you should look for a Russian one, Latvian one, Czech one, I don't know. If there's none, well, you're probably just left with a blank page and you have a start on yourself. But I don't think there's any Polish grammar included in LTK. I wouldn't say no. Yeah.
Are there any libraries that support Polish grammar or Polish language processing?
In Python, I'm not aware of, no.
Thanks.
Thank you.